Good afternoon, class. I hope you're doing well. Um, I have a lesson for you today that is rich in theoretical exposition. So I know you're going to love it. So what we're going to do today is learn about something called length contraction and time dilation. So after my lessons yesterday, I was forging for about 5 hours. And actually, the joints in my hands just hurt from like holding the hammer and holding the tongs, and so my hands are pretty sore. But the tongs I have are really bad because they are like, this is how they close, kind of like this, and so they're fine at holding things if the thing you're holding is thin. So I could hold something thin like a cell phone, for example. But if the thing you're holding is like round, you try to pinch down on it and it just shoots the thing out, right? So I was trying to make my own tongs, and it didn't go so well. This is what I got so far. It was like I needed the tongs to make the tongs, right? I couldn't hold this piece of steel and it kept slipping. And when you hammer the steel, so if I'm hammering right here, boom, 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 it bends up like this. So the more you hammer it, the more warped it gets. And then you have to get the warp out. And I was just having a heck of a time. I was cursing up a storm. Bug hates it when I start yelling, and he just will go into a corner and just start trembling. He's just like traumatized so much. So yeah, that was my day yesterday. But I'm not giving up. This is the important point. I will make my tongs. One of the things I like about forging, it's kind of the same reason I like painting or drawing, right? It's like if you screw up a painting, don't panic, just paint over it, right? If I screw up forging, don't worry, just get it hot and hammer it again. It's going to take a new shape. So I'm not that discouraged. But I was just tired yesterday. All right, let's see. Who do we got here? We got Luigi, Rowan. Hey Luigi and Rowan. Hey, Zach. Hey, Wahlberg. Hey, Watkins. Finalement, Justin dit quelque chose que je comprends. Donc, je dis à toi, ça va? Something like that. All right. So let's get into the theoretical exposition. All right. This is gonna be fun for me. I don't know. Maybe you won't find it very fun. So we would. I want to remind you of the equations that we learned yesterday. So the equations we learned yesterday were these ones. Yeah! All right. And so we have two events 1 and 2. And those events have a certain separation in space and a certain separation in time. And so depending on the observer, they have a different separation in space and a different separation in time, okay? And that's what this expresses. So I would like to give you guys a theorem. And someone spoke more French to me. Je pense qu'il apprend pas. Oh, Rowan, your French was really bad there. It's je pense qu'il n'apprend pas de français. It's always pas de, and there's a ne in there, so you totally messed that up. So the theorem is that the theorem is that if we have the space-time interval is invariant. So no matter who you are, if you're observing the same two events as everyone else, no matter how fast you're going where you are going to calculate the same space-time interval. Okay? So that's why the space-time interval is so important, because no matter who is measuring it, they always get the same answer. Okay? So I'm going to prove that. So what would be delta t prime squared minus delta x prime squared? Okay? Well, I'm just going to plug in these two formulas for delta t prime and delta x. So we have gamma delta t minus gamma beta delta x minus gamma beta delta t plus gamma delta x. Okay, so I plugged in the formulas for delta t prime and delta x prime that come from the Lorentz transformation rules. And now I'm going to FOIL each one. So I have to do two FOILs. So I have gamma squared delta t squared. That's the first term. The last term is gamma squared beta squared delta x squared. And then the cross term is minus 2 gamma squared beta delta x delta t. Okay, so that's squaring the first term. Squaring the second term, and remember we're subtracting those two, so I'm going to add an extra minus sign. So I have minus gamma squared delta x squared minus gamma squared beta squared delta t squared. So this is the last term squared. This is the first term squared with an extra minus sign added in. And then the cross term is plus 2 gamma squared beta delta x delta t. Okay? So what we notice is that the cross terms cancel out. Okay? Now I'm going to collect the delta t squareds and the delta x squared terms. Okay? So I'm going to get, for the delta t squared, I'm going to get gamma squared times 1 minus beta squared delta t squared minus minus gamma squared 1 minus beta squared delta x squared. All right. Now here's the fun thing, is that gamma is 1 over the square root of 1 minus beta squared. So that means that gamma squared is going to be 1 over 1 minus beta squared, which is exactly what would be needed to cancel out 1 minus beta squared. See? So we get delta x, or delta t squared minus delta x squared. And that's what we wanted to prove. Boom. So all observers calculate the same space-time interval between the same two events. Okay? So that is why the space-time interval is so important. Okay? So now, what I would like to do, are you guys familiar with the Silver Surfer? I kind of want to wait, but Wahlberg asks, do I prefer a black box or QED to end proofs? I prefer a black box. So if you don't know who Silver Surfer is a character in Marvel Comics, and usually he's with the Fantastic Four, but he basically is a dude who's all silver, and he rides through outer space on a surfboard. Okay? And he is the Herald of Galactus. So Galactus is this giant supervillain who destroys entire planets, and Silver Surfer flies to the planet first, and he says, I am the Herald of Galactus. Galactus is coming to destroy everything. And then Galactus comes and destroys everything. But, Silver Surfer feels bad about having this job, and so eventually he revolts and tries to kill Galactus. And this is part of it's not really in the Avengers timeline. It's like a separate Marvel timeline. So yeah. So anyways, what I would like to do is I would like to imagine the following scenario. So what if the Silver Surfer is on his surfboard, okay? And you are holding up your hand, okay? So you're like this, okay? And I'm going to make his surfboard longer, okay? So here, and the Silver Surfer is headed this way with velocity v, okay? All right, so event 1 is when the tip of the surfboard, the front tip of the surfboard hits your hand, okay? Event 2 is when the back tip of the surfboard hits your hand, okay? So Silver Surfer is doing a flyby. So that is event 2, all right? And so we're actually going to use this scenario to derive the formula for length contraction. Okay? So here's how it works. We're going to use the invariance of the space-time interval. Now, the Silver Surfer is the primed reference frame. And you are the no prime reference frame. Okay? So we have delta t prime squared minus delta x prime squared equals delta t squared minus delta x squared. All right? So the right-hand side is the separation between the events according to u, the unprimed, and the right-hand side is the separation between the events as compared to the Silver Surfer. Okay? So what is the spatial separation between those events according to you? All right? What is it? Well, you're just holding your hand up. So it's when the front part of the surfboard hits your fingers and when the back part of the surfboard hits your fingers. So both events happen at the same place, according to you. They both happen at the tip of your finger. So the delta x, according to you, is 0. Okay? What is the time? What is the time between the those two events, according to you? Well, it depends on the length of the surfboard, right? So you know that velocity is distance over time, right? The surfboard is going at a constant velocity. So the time between those events would be L over V. All right? So according to you, the time between the events is L over V. So we have L over V quantity squared. All right? Now, if we think about this according to the Silver Surfer, from the Silver Surfer's perspective, the Silver Surfer looks down, and from the perspective of the Silver Surfer, it is not the surfboard that is moving, it is your hand that's moving, right? It's like if you're on a train and you're looking at a light pole or something. From your perspective, it's not the train that's moving, it's the light pole that's moving towards you and going like that, okay? So according to the Silver Surfer, the first event happens at the front of the surfboard, and the second event happens at the end of the surfboard, okay? So the distance between those two events is just the length of the surfboard, which I'll call L prime. And the important point is we can't assume that the length the Silver Surfer measures for the surfboard is the same as the length that the person measures for the surfboard. Okay? By a similar logic, the time between those events. So again, the Silver Surfer doesn't see the surfboard moving. What the Silver Surfer sees is your hand going like that. And how fast is the hand approaching the Silver Surfer? Well, the hand approaches the Silver Surfer with speed v. Okay? It's kind of like if we have two things that are headed towards each other in outer space, from my perspective, it's you moving towards me, and from your perspective, it's me moving towards you. Okay? And if you were truly in deep space, there would be no way to tell the difference. There would be no way to tell who's moving and who isn't moving. Okay? So the time between the events, according to the Silver Surfer, is going to be L prime over V. All right? Now, I'm going to spare you the algebra. But what it ends up showing, if you work out the math here, is it says that L prime over gamma equals L. All right? And remember, gamma is always bigger than 1. So the bigger than or equal to 1. So the what that means is that, so remember, L is the length of the surfboard according to you watching the surfboard fly by. Okay? So you're dividing by a number bigger than 1, which means that if you're watching the surfboard fly by, it appears shorter than if you were standing on the surfboard. Okay? So this is called length contraction. All right? So L prime is the length measured when at rest with respect to you. And L is the length when moving. All right? So in fact, and the faster something goes, the more the length is contracted. Okay? In the limit that the thing approaches the speed of light, the length of the surfboard would actually go to 0. Okay? So it's a real phenomenon. It's called length contraction. So that's a pretty cool thing. And so the next thing I want to talk about is something called time dilation. Okay. So again, let's consider the Silver Surfer. Okay. And the Silver Surfer is holding a clock. Okay. And so event 1 is the clock ticks. Okay. And the Silver Surfer is moving with a velocity v. Event 2 is the clock ticks again. Okay? So the first event is the first click, or the first tick of the clock, and event 2 is the second tick of the clock. And what you're going to do, you're watching the Silver Surfer, and you have your own clock. And so you are going to look at your own time in between the two clicks. Okay? So again, we're going to use the invariance of the interval to figure out how these two things are related. Okay. So remember, the Silver Surfer is with the prime, and you are with no prime. So what is the spatial separation between the events according to the Silver Surfer? Well, the Silver Surfer is just looking at the clock, and he's just holding the clock. So according to him, the clock isn't moving. All right? So delta x is 0 between these two events according to the Silver Surfer. What is the delta x between the events according to the person who's watching the Silver Surfer? Well, the Silver Surfer is flying by, so the clock ticks once over here and again over here. So we can use the same logic as we did in the previous one to figure out that that delta x is just t over v. all right? And the person measures the time interval between those events to just be t, all right? Now, the Silver Surfer is going to have a different amount of time between the two events, which I'll call t prime. So, again, we have different time intervals. We can't assume that the time between the clicks is the same, okay? I'll spare you the algebra, but what it says is that t prime times gamma equals t. All right? So remember, t prime is the time according to moving thing, and t with no prime is the time according to the stationary thing. Okay? And gamma is greater than 1. Okay? So what this says is that if you are moving, less time elapses than if you are stationary. Okay? Fast clocks tick more slowly. And so this phenomenon is called time dilation. All right? Time dilation. So time dilation is also a real thing. We observe time dilation most commonly in decays of unstable particles, okay? Because if you have an unstable particle and it decays, it will blast off a piece at close to the speed of light, okay? And when an unstable particle decays, it often decays into additional unstable particles. So you have this cascade of decays where the first particle decays and it shoots off a particle, and then that one decays, okay? And what we find is that the faster the particle gets shot off, the greater speed with which it gets shot off at, the longer time before it decays. Again, so that's a manifestation of time dilation. We've also taken really sensitive clocks and flown them around in airplanes, and we find that not as much time passes when it's flying around on the airplane. So it's pretty cool. Satellites as well. You can correct for time dilation with satellites with very precise clocks, because a satellite is going to be moving really fast at kilometers per second. So what they do is they actually, when they build the satellite on Earth, they make its clock intentionally tick too fast. So once the clock is, if the clock is on Earth, it's not going to sync up with Earth clocks. But once it's in outer space in its orbit and it's moving fast, the clock now is in perfect sync with Earth. Pretty cool. The other thing is, why don't we notice length contraction or time dilation in daily life? It's because gamma is approximately 1 if you're not going close to the speed of light. So if you're not going close to the speed of light, then none of this matters, okay? The two lengths are the same, the two times are the same. It's only that once we start approaching the speed of light that these effects become significant. I'd like to do a little example, okay? All right. Let's say we have a spaceship travels to a star 8 light years away with speed 0.999 c. So 99.9% the speed of light. Okay? People on the spaceship measure it to be 130 meters long. So, and then Earth observes the journey of the spaceship. Okay? First thing I want to know is how long, right? I have to be specific here. How much time does the journey take according to people on Earth? All right? How much time does this journey take according to the people on Earth? Well, according to the people on Earth, the spaceship is basically going the speed of light. Not quite, but almost the speed of light. Okay? So how long would it take light to travel 8 light years? It would take 8 years. Okay? So the time that the Earth is going to see this spaceship taking to go from point A to point B is going to be approximately 8 years. It'll be a little bit longer than that because it's not quite going the speed of light, but it's going to be pretty close to the 8 years. So now we want to know how much time does this journey take? According to people on the spaceship. All right. Well, we better figure out what gamma is. Gamma is going to be 1 over the square root of 1 minus beta squared. Beta is 0.999. So gamma is 22.3. And so if you were on the spaceship, time is going more slowly for you. So it won't take a full 8 years. It'll take less than 8 years. So we're going to take 8 and divide it by 22.3. See? So T is the time according to the stationary thing, which is Earth in this case, so that's 8 years. Gamma is 22.3, and we can calculate T prime, the time according to the moving thing. So we divide by 22.3, and we get 0.35 years. So that's about a third of a year. So that's roughly 4 months. So if you were on this spaceship, only 4 months would elapse. Okay. This is kind of a cool thing, right? Like weird stuff could happen. What if you had what if there was a child, okay, who was, let's say a child is 9 months old. No, let's say that the child is 5 months old. Okay, and then there's a newborn baby who's 0 months old. Okay, so the newborn baby is the younger brother. Okay, there's two boys. Now, what if the 9-month-old or the 5-month-old baby goes on a trip to this other star? When they arrive, the 5-month-old would now be 9 months old because the journey only took 4 months according to the baby who's on the spaceship. But the one who was a newborn baby, the 0-month-old, would have aged 8 years. So basically the younger brother becomes the older brother during the journey. It's pretty trippy. And this happens in the movie Interstellar as well, right? It's the daughter becomes older than the father. So this is a trippy relativity thing. Last part of the question: how long would the spaceship appear how long would the spaceship appear according to observers on Earth? Well, so according to observers on Earth, the spaceship is going to be length contracted. So it won't be 130 meters long. It'll be 130 divided by 22.3. So it would be 5.8 meters long. So it would be a very sort of chubby spaceship. Wahlberg asks, wasn't that from the gravitational field of the black hole? Yes. So going fast has the same effect of slowing down time as strong gravitational fields do. Now, one of the things I think is interesting, if I could just, I'm done with the content of my lesson, so I'll take away the piece of paper. But if anyone's ever read the novel Ender's Game, in Ender's Game, there's a war, and there's a general who figured out how to defeat the enemy. Okay, but they didn't completely defeat the enemy. So there's this military genius who defeated the enemy, but they know that the enemy is still out there and probably there's going to be another war. So what they do is they take the military genius and they put him in a spaceship and they make the spaceship go close to the speed of light. And what that does is it basically preserves him so that from his perspective, the war just ended. But then, like 100 years go by or something. And then when the second war happens, after a long, long time, they slow him back down again and they can use him again in the second war. So it's a way of preserving things. I think I probably mentioned this before, but I think our economy would collapse if we could go close to the speed of light because money sort of has no meaning anymore. The stock market has no meaning anymore. Like if I could go close to the speed of light, I would put a little bit of money in the stock market and then I would go close to the speed of light. And, one day would go by for me on my spaceship, but maybe 50 years go by on Earth. And all that time, my money in the stock market has been exponential growthing. And I'd be a rich man when I came back. So I actually have an idea for a short story based on that idea, where we figure out how to go close to the speed of light, and then a bunch of like bankers and stuff, they go up into outer space, and they all start traveling close to the speed of light so they can all get rich. But then, as a result of everyone going up into space, the entire economy collapses and money becomes meaningless. So they come back and it doesn't matter. So, anyways, that's my lesson for today. I will see you tomorrow. Oh, and I haven't put the daily